So, good morning, students. So, I welcome you in the lecture series of digital time signal processing subject. So, let me choose a pen. So, in this particular, just a minute, I will take a pen of different color. So, in this particular lecture, we will discuss about the fast Fourier transform. Okay, this is nothing but the FFT, fast Fourier transform. Till that, we have seen the DFT. Okay, DFT, that is nothing but the discrete Fourier transform. Discrete Fourier transform. This is required for computation of any process. If you want to compute something, then we have to go for the discrete type DFT, that is discrete Fourier transform. But some disadvantages are there as far as complexity is concerned. So we have to move toward the fast Fourier transform. The motive of this DFT and the FFT are the same one. Means we are obtaining same result as far as FFT is concerned and DFT is concerned. But the time and the multiplication and addition that operations are required, that are more one. For example, what we are doing, we are suppose we know that the summation x of n, we are writing it like this one, x of n e raised to minus j 2 pi k n upon capital N. Okay, capital N. So for 8 point DFT, what we are doing, 8 point D, we are calculating x of 0 to x of 8, up to 8 we are calculating. But in this also, what we are doing, we are writing x of 0 plus into e raised to 0 plus x of 1 e raised to again 0 if I am putting the value of small n is equal to 0. So for this case, 1 multiplication, okay, like this one, 2, 3, 4, 5, 6, 7, 8 multiplication and 7 addition for one equation required, means 7 8 multiplications into, for 8 point we have to calculate, that is nothing but total 64 multiplications are required. And what about additions? So 1 less than required, so 7 into for 8 point we required, so 7 into 56, so 56 additions are required and 64 multiplication required for 8 point. So now keep in mind our sequence, whatever if I am talking on with you guys, so that is a stream of data, stream of bit of data. Normally if 1 2 3 4, this is it's okay, it's an example, okay, 5 6 7 8, this is the example, just 8 point. So keep in mind, if I were to go for the 64 bit data, then 128 bit data, then 256 bit data, so the lot of complexity and calculations are required for this. Okay, for normally this DFT and calculated by the computers, so it will require more time to calculate the data. So more time calculated data, and single operation it perform within 1 or 2 days. So to reduce the complexity, we have to go for such algorithm which will require the time complexity of the algorithm and obtain the same result, that is nothing but algorithm is nothing but the fast Fourier transform algorithm. Okay, are you getting what I am trying to say? Okay, give me thumbs up in the chat box. So DFT, what we are doing, I have explained this thing, that is nothing but, if I want to take the DFT, okay, I want to take now pen of black color, I will choose the pen black color, yeah. So we are having x of k is equal to summation small n is equal to 0 to n minus 1. This is length of sequence, okay, means how much point we are calculating, 8 point, 4 point, 16 point, 128, 256, whatever. So I have to put this one, and x of n is my sequence, and n is nothing but the what of point I am calculating, e raised to j 2 pi n k divided by capital N. This is nothing but this n and this and the same. If I want to take the in the frequency domain, I have to use this formula, and if I want to take the inverse DFT, then I have to use this formula to calculate this one. So to require the complex multiplication, I require what? How much? N square, that we have seen in the previous slide. That is nothing but, if n point is there, n into 8, n into n means n square is nothing but how much? 64 multiplication required. And as far as additions are concerned, n into n minus 1, that we have seen, that is nothing but n is 8 into 7, how much? 56. that number of complexity or complex operation we have to perform in a single calculations. So to avoid this thing, what we are doing, we have the second alternative is nothing but what? That is nothing but what? FFT, that is nothing but the discrete fast Fourier transform. This is the option for this one. So we are having this thing with you, that is nothing but we are having this formula. Just a minute. Yeah, we are having this formula. So I will write this W is equal to e raised to, I will write over here, already written over here, that is nothing but I will write W is equal to W n k, this n, this formula, this particular formula, this formula we will try to rewrite this particular value of e raised to, how we are particular, and this is called a twiddle factor. How I will tell you what we are doing in this one. So here n, so say this is W n, and here I will write the value of k. Here I will write the value of k over here. Okay, that means this W, not just single W, is equal to e raised to minus j 2 pi n only. What is W means? E raised to minus j 2 pi k n only. And if I am writing k, so I have to multiply. Okay, k is already there, so no need to write e raised to minus j 2 pi only. Okay, so 2 pi n only, n, j, forget about this. Then if I am writing this, I am just repeating once again for you guys, just remember. So W is equal to e raised to minus j 2 pi small n only. Okay, and divided by nothing is there. If I am writing here k, so I have to multiply k over here, and here if I am writing n, so I have to write n over here. So the W twiddle factor, it is given by this formula only, e raised to minus j 2 pi n only. Okay, and if I am writing like this one, so it is nothing but. So what is the idea behind this one? What is the idea behind this one? Is nothing but what we are doing. We have to divide this algorithm. Suppose 8 point is there, 8 point algorithm is there. So I will divide it into two parts. That is nothing but the sequence of odd part and sequence of even part. Sequence of odd and even terms, that is nothing but odd contain 1, 3, 5 and 7 part, and odd contain including 0, even contain 2, 4 and 6. So we are treating this part separate and we are treating this part as separate, and we are doing this thing. Okay, so very good. Sure. Next, so what we are doing this thing, as I am having x of k. Now concentrate very carefully. As far as FFT is concerned, there are two domains, that is nothing but the discrete decimation in time, DIT I will write, and decimation in frequency. So this technique is different one and this technique is different one. I will in the next lecture I will cover this topic on the blackboard. Okay, with the help of problem. If problems I am taking, then you are getting the okay, it's a very easy thing. But as far as the theory is concerned, you require more and more concentration. So we are having this formula, that is nothing but x of k is equal to small n is equal to en minus 1 x of n w, that is twiddle factor. This is twiddle factor n k and n. So this w here, this w can we decode the w? Just a minute. Can you decode the w? So this w is nothing e raised to minus j 2 pi only. Okay, so w is equal to e raised to 2 pi. If I am suppressing this n also, so e raised to minus j 2 pi is only. Okay, so this w is nothing but e raised to minus j 2 pi. So I have written this thing. This formula and the previously formula I have shown is one and the same one. Okay, so what I will do, I will take first even part. For n is equal to even, x of n w of n k plus some parts are even, n is equal to means I will put n is equal to what, even in 0, 2, 4, 6, and here odd 1, 3, 5 and 7. Like this one I have divided first formula into this. So as far as this capital N value is there, that is always n minus 1. So n by 2 I have divided even part and odd part, that's why I written n minus n by 2 minus 1. So r is equal to, that is what I have, why I am using r, because I have divided my n into odd and even. So x of twice r. Why I have add twice r? Because it is even part, and as far as odd part is there, what I will do, I will add twice r plus 1 over here. Okay, twice r plus 1 over here. Yeah, are you getting? Okay, very good. So just a minute, I will rub this portion again. Okay, so I have written this thing. Then this part is also there. I have written is the value of n is equal to 2, and here n is equal to also 2. So I will get these two parts in the time domain. So now what I have to do in this particular case, what I have to do, I have to take the even part as g of k, and odd part, that is nothing but the h of k, and odd part I have multiplied with the dual factor, that is nothing but the w k n. This part you will get absolutely clear in the what problem. If I am talking about the problem, if I am solving the problem, you are getting everything crystal clear, that is I am sure, because theory part is there, so some kind of confusion is there in your mind. Okay, and nobody is asking about the theoretical concept of this is entirely problematic subject. 95% you will find only problems. 80 out of 80 mark question, you will at least you will find 70 marks problems only. 70 marks problem, and whatever the theory is there, that is all about derivations only, that is the property, derive this property and all that. No one will ask you explain this DIT algorithm to you. So this is the odd part, this is the even part. Okay, n by 2 dft, n by 2 dft, and this cross and all that we will discuss in the upcoming lecture one. Okay, so till that, thank you very much for attending this session. Thank you.